Okay, so today we'll be discussing week 5 discussions, and week 4 I said that I will discuss how to use Newton method for the multivariate optimization. So first we'll discuss one example for that, and then we'll go on and discuss about quadratic approximation, and one example for unconstrained optimization. Okay, so yeah. Let's start with the Newton method. So here we have a function in x1 and x2. The function goes on like x1 minus x2 plus 2x1 x2 plus 2x1 square plus x2 square. Now we have to, in this function, let's try to do this. Let's get the direction for the first step in the optimization using Newton's method. So, as it was discussed in class, that when we have to do optimization for using Newton method, so for optimization, and I have also discussed this in my previous videos, that then the next step xn plus 1, let's call it, will be given by xn plus 1 is equal to xn minus f dash of x divided by f double dash x. And when we are trying to find out the root, in that case xn plus 1 will be given by xn minus fx divided by f dash x. So if you remember, I said that one trick to remember or to simply learn this is, when we are doing the optimization, we want the gradient to be 0. So we want f dash x to be 0. And when we are doing the root, we want the value of the function to be 0. So whatever comes in the numerator of this side, on the RHS side of this expression, is going to be equated to 0. So when we have optimization, f dash x will be 0. When we have root, fx will be 0. Okay, so now let's start with this problem. When we have when we have multivariate, then of course we'll need to have a matrix multiplication. So we will have something like x1 k plus 1 x1, sorry, x2 k plus 1 is equal to x1 k x2 k minus inverse of the Hessian matrix multiplied by the gradient of the function. So this is what we are going to use. Okay, so let's solve this question. Let me just write what our fx was. So our fx1 x2 is x1 minus x2 plus 2x1 x2 plus 2x1 square plus x2 square. Hey, hey Diksha. So was Rito's session going on for this long?
Yes, sir.
Oh, okay. So I thought probably you guys are not going to join because of the today's the nature of the assignment. So I started. Okay, so okay, maybe I'll s- I'll tell you what I was discussing. So yeah, last time in the lecture we were trying to do the multivariate optimization. So I discussed the problem. So I discussed the problem with two methods, the steepest descent and then the other one. But I didn't discuss for the Newton method because I said there will be, yeah, there is some confusion how to use the Newton method for using the delta approach that sir discussed. So you know, so I so today we will be discussing how to use the Newton approach, but I'm not sure that we can actually use that delta approach, like the discretization using f of x plus delta x. So we'll just use plain old normal differentiation, and we'll see one example for the Newton method. So basically, I have discussed is for optimization. The next step of our root will be xn plus 1 is equal to xn minus f dash x divided by f double dash x, and for root we have just the fx divided by f dash x. So yes, and then for our particular multivariate optimization, we will need a Hessian matrix, and we will need a gradient of the function. So yeah, let's go ahead and solve this question. Okay, so we have our fx1, fx2. So this is x1 and 2. So let's make the gradient. So it will be df of dx1, df of dx2. So if you can do with me, the question. So you can also tell if I'm doing some mistake. Yeah. So we have differentiation of this function with x1. So 1 plus 2x2 plus 4x1, and then differentiation with x2 minus 1 plus 2x1 plus 2x2. Is this correct? Okay, I will take it as a that it is correct. So and we'll proceed with the other one. So we have d2f by d2x1 square. It is going to be 4 from this one, and d2 by dou, actually it should be, I should call it dou for accuracy, for correctness, because it is a partial derivative. So dou 2f by dou x2 square is going to be 2, and dou 2f by dou x1 dou x2 will be 2. So you can check from both the expressions, it is going to be 2. That means our Hessian matrix is going to be, let me just write. So this is our Hessian matrix, which will look like 4, 2, the diagonal values, and 2, 2, the non-diagonal values. Okay. So our Hessian matrix doesn't depend on x1 and x2, so that's a good thing. But still, we need to calculate our gradient of f at x1, x2 for x1, 1 and 5. If I'm not wrong, it is 1 and 5. Yes. So let's calculate. And if I'm doing wrong, I would really appreciate if you can stop me at my tracks. Yeah. So 1, 2, and 4. So basically, let me, yeah. 1 plus 2 into 5, 1 plus 2 into 5 plus 4 minus 1 plus 2 into 1 plus 2 into 5. So this is 10 plus 1 plus 1 15, and we have 10 plus 1 11. So I hope this is correct. Yeah, so let's go on and get our first step. So x1 will be x naught minus, as I said, inverse of the Hessian matrix multiplied by the gradient of fx1 gradient of f at particular x naught. Oh, sorry. Yeah. So we have 1 5, and okay, so I don't know if you guys know this trick or not, but for a 2 by 2 matrix, uh, can anyone tell me what will be the inverse? So there are only two of you here. So yeah.
You change the signs and invert the elements of diagonal.
Okay, so you are saying it should be b a and minus d minus c. Is that what you're saying,
Something
Jason?
like that.
Sorry.
I think so, yeah.
So yeah, so this is correct. But one thing we are missing here is we have to divide by the determinant of a. So this is one short trick that you can remember if you didn't know that. So now you know. So h we had was 4 2 2 2, and determinant was 4 into 2 minus 2 into 2. So that is, determinant was 4. So that means h inverse is going to be 2 4. We, what do you say, we flipped the diagonal elements, and then we change the direction of change the sign of the non-diagonal elements, and then we divide everything by the determinant. So let's just not divide it and make it into decimal places. We'll just keep it like this. So we have our x naught minus the inverse of the Hessian matrix and our gradient of f fx at x naught. So if you multiply this, can you tell me what will be the order of the matrix after we multiply these two matrices? So let me just make it clear. By
2 by
order.
1.
Yeah, correct. Thanks. Yeah. So I just want to make sure that you guys are actually listening. So I'll ask some very stupid questions also. So don't mind me. So okay, so we have multiplication. We will multiply 2 into 15, 30, and minus 22, and then minus 30 plus 44. So we have 1 5 minus 1 by 4, 8, and 14. So basically, uh, what we want to do is we will get our x1 again, and then we repeat the same process of finding the. So we already know that our Hessian matrix doesn't depend on x1 x2, so luckily it will not change. Just our gradient will change with the values of x1 and x2. So we'll find the gradient again with these values that we'll get after simplifying this, and then we can go on until we get a converged value of x, or we get a, when we get the converged value of x, that means this this side, this particular side will be converging to 0. So those are the criterias that you can use. So for now, if I ask you that tell me what is the direction in which we should go for the first iteration, so what would be your answer? Because generally solving all this throughout, it's going to be a lengthy process. So if they ask what is the direction in which we should go for the first iteration, what will be your answer? Okay, so do you guys remember that in the step by step method, or even the steepest gradient method, what we did was we had our x is equal to x new, x old, minus some distance and some direction vector and then some distance vector. Do you remember this? So let me erase this from here, since I didn't know that I will take this much space. So I ended up making less number of slides. So I might have to erase some of these things. Yeah. So if you remember, if you don't remember, let me say this. So we had our for single direction univariate method. What we did was we decided to go into the x direction first. So we had our direction vector as 1 0, and then we put the value of x new into the function x old plus alpha into d. We put this value into our fx. Then we made the differentiation of fx new is equal to 0, and when we did that we got the value of alpha. So we need to go in certain distance in x direction. So if this was our contour of the function and this was our minima, and let me use a different color, and this was our starting point, then we chose to go in x direction first. So if we get some alpha, we'll go in x direction. Then we chose to go into the y direction. So we had our direction vector like this. Then we got some alpha and we went into this direction. So like a step, we are approaching to the optimal solution. So in that case, we already decided the direction in which we wanted to work on, and that's how we approach the problem. But in the steepest descent, what we get is if we have a two variable problem, then we give the direction, we get the direction in which we should go to get to this point the fastest. So let's say in the steepest descent, when you have a nice simple curve and you have a starting point here, what it will give is this direction. So instead of going like step, you will go directly to this direction. It will give you some alpha and will reach the solution in one step for this particular problem. Similarly, Newton-Raphson also does the same thing. So we have Newton-Raphson. You can assume that we gave our d as 1 and 1, and we got some alpha. So alpha d was the direction that we should approach for getting to the optimal solution fastest. So the answer in single words, so to speak, for this question, that which direction we should approach in the first step to get to the optimal, is going to be with minus sign 1 by 4 8 14. So it should be minus 2 minus 3.5. Is this clear, Jasurya?
Yes, sir.
Okay. Okay. So now let me go to discuss this week's session, this week's problem. So we discussed quadratic approximation. So basically what we want to do is we want to approximate a function in quadratic form so that it is easier for us to solve and get the optima. So what will be the quadratic approximation for this particular function? So let's start. Basically, if we are aware of the Taylor series, that is, let's say f of x plus delta h. If we want to know the value of f, the function f at x plus delta h, and we know the value of the function f at x, then we can write this, and it is universally true. Any function you want, you can write in this particular fashion. It can be written as f(x) plus delta h f dash x plus delta h square by 2 f double dash x plus delta h cube by 3 factorial f. So this is factorial. 2 factorial is 2, 1 factorial is 1, so we don't write it usually. And also, Jasurya, can you tell me the value of 0 factorial?
It's once.
Yeah, perfect. So yeah, so it goes on like this and it goes to infinity, and the more terms you include, the more accurate representation of f of x plus delta h you will get. So when we say quadratic, what we mean is we are going to limit ourselves to only second power of delta x square. And when we say quadratic approximation, then so quadratic approximation of fx at x naught. So basically what we mean is our fx, and we are saying that fx is almost equal to fx naught. Then this is our remaining term. So let me just write it here. So we are doing the optimization and we want to find, let's say, maxima or minima. For now, let's consider minima. And then we are saying that the minimum value of fx is actually fx naught. We are trying to say this. But we know that that's not the case. When you open it using the Taylor series, you know that there are some other terms also that will proceed after this. So how do we make sure that our fx is actually equal to fx naught for that particular x naught? So what we do then is our aim changes from minimizing fx to minimizing this particular function. So this is our new thing that actually we are going to minimize. You can write delta h as x minus x naught, and you can replace this particular function as, so I will write it as x naught here, so to avoid any confusion later on. So we minimize our this particular function so that we can confidently say that actually we have approximated our fx to fx naught. And that's what happens when we minimize this value will particularly go to 0 or some other value, and we get our optima at x naught. We get x naught, so we iterate for x naught. So, but in this question, actually, I got a little bit sidetracked. We are asking about what is the quadratic approximation of fx. So let's try to write this, and Jaisure, you can also write, so that if I do something wrong, then probably you can help me say that you're doing
Sure,
wrong.
sir.
Yeah. So we have our fx e power x sin x, and our x naught is 0. So let's write e power x, that x naught, and then x minus x naught. So what is the differentiation of our, so let me first write the differentiations. So using the multiplication rule, e power x is e power x differentiation, and sine differentiation is cos. So, and then our double differential, it will be e power x sine x plus cos x e power x, and then this one minus sine x e power x plus cos x e power x. Is this I don't think this is what do you think, Jayasuriya, is this correct?
Yes, sir, it's correct.
Okay, are you sure?
No, sin x, cos x, sin x. Yes, sir, I think so.
Okay, so let's proceed with this. So we have f double dash x and f dash x. So then f dash of x naught, so we will have e power x naught sine of x naught plus cos of x naught. Then we have 2 into cos of x naught e power x naught. So when we put the value of x naught is equal to 0, we get the approximation sine of 0 is 0 plus x minus 0 is x, then e power 0 is 1, and multiplication with again 0 and cos of 0 1, we have x plus x minus, oh so this is square, so this I wrote wrong, x minus x naught square is x square, and then we have into 2, and cos of 0 is 1 and e power 0 is 1. So we have our solution as x plus x square. So is this what you got, Jay Surya? Do you think it is correct?
Yes, sir.
Yeah. So this is the correct answer. So this is the quadratic approximation for this particular function. But we have to remember this, that now to, yeah, to solve this we actually need to minimize this particular value rather than this value. Yeah. Okay, so now let's go to a different problem and try to write the quadratic approximation for this. So yeah, why I chose this problem is, when we are in the class also, sir showed a little bit simpler problem for solving and showing the use of quadratic approximation. But I was thinking that that problem we can even do by simply using Newton-Raphson. Why do we have to do quadratic approximation? So the problem which are like this, for these particular problems, it is, I think it is better if we use some kind of approximation. So Ajay, I just wanted to highlight that it's just not in vain that we are studying this quadratic approximation. There are some cases where we can actually use it and it will be beneficial for us. Yeah, so we have, yeah, so again I will request Jesuri if you can do with me, or you can check what I am doing is correct or not. Yeah.
Okay, sir.
Yes. So let's do it together then. Fx y is, so let's directly write f dash of x. Oh yeah, and in this particular problem, I should have mentioned this. We would probably need a Hessian matrix, right? So yeah, I don't know why it is not selecting this. So let it be. So for this particular kind of problem, what we needed was, I think it was shown in class, is f of x is equal to f of x naught plus x minus x naught, then our gradient of xy plus x minus x naught, Hessian matrix, and then x, so 1 by 2, I should keep it here. So is this correct, uh, Jasurya? What do you think? Is this the notation that we should use?
I can't remember it from class, sir, but I think it does. I remember it being a Hessian matrix.
Yeah. So we can actually do the cross verification. Hessian matrix is nothing but double differentiation. So
Yes.
if we remove these things, the y, then it will boil down to this particular differential. And this thing is nothing but, for matrix multiplication we have shifted them on the left and right, but they are nothing but x square. So no, sorry, x minus x naught square, and then we have the 2 that we already had. So I think this is the form which we can actually check by simplification. And let's go on and let's do the solution for this problem. Okay, so okay, so I think I have not corrected this here. It should be x naught, capital X naught is 1 and 1, the initial point. So let's get the gradient of fxy. So first we'll differentiate it with respect to x. So 5.5, 4.5 plus 2 and 3.7 y power 2.7. And this particular value at x naught, capital X naught, is going to be nothing but 7.5 divided by 3.7. So is this correct?
Differentiation is correct, sir. The value I have to check.
Okay. No, so that's why for simplicity I have given x value as 1 and 1 and y value
Yeah,
as 1.
then it is
Yeah.
simple. Yeah, it's correct. It's correct.
Yeah. So okay, now let's go on and find out the Hessian matrix. So for Hessian matrix we need double differential. Okay, so it's first time for me to use this iPad, so I apologize if this is irritating. I don't know any
No,
other
sir, yeah.
software. Yeah. So this is our dou f by dou x. Now we want a double differential, so we need to differentiate again this with respect to x. So 5.5 into 4.5 to x power 3.5, and then dou f by dou y square, it's going to be 3.7 into 2.7 to y in power 1.7, and the 0 is gone. Yeah, so the 2 is gone here. Now the non-diagonal term of the Hessian matrix, that is dou 2f by dou x dou y, is going to be 0 because,
0.
yeah, correct. So we got our Hessian matrix. So let's make the Hessian matrix here itself, and in the next one we'll simplify that. 5.5 into 4, sorry, 4.5, 3.7 into 2.7, 0, 0.
24.75 and 9.99.
Yes, so 24.75 and 9.99.
99.
So yeah, thanks. Now we have our h, and now we can successfully write our uh, this particular quadratic approximation. So f of x1, f of x is equal to f of x naught. So then we'll have to put the value into this expression. It will be nothing but 1 plus 1 plus 2.
It's 2.
Yeah. So f of x naught, which is 4, plus x minus x naught. So it will be a vector x y minus 1 minus 1. It's a transpose, and then our this particular gradient, so it will be 7.5 and 3.7, and then plus x minus 1 y minus 1. So 24.75, 9.9900, and I am not sure about the order, but for them to be multiplicable, I think it should be like this. So 2 cross 1. Okay, no, it should be opposite actually.
So
So
the horizontal should come first.
yeah, so it will be, let me write it like this, or maybe let me write it differently. Okay. So Jesuri, can you tell me this approximation? I will just be I'll be back. I am getting a call actually. 1 minute. Thanks. आप अपन मस्त क्लास ले रहा हूँ मैं। पहुँच गए कि नहीं पहुँचे आप? ट्रेन में बैठ के चलिए करता हूँ बात में। हाँ। Okay. Okay. So yeah. So I think here also the horizontal should have come first. Yeah. So it will be 1 comma 2. No. So it should be y. So then I think it's a nice expression coming along for us. Something like this. So what do you say, Jesurya? I don't think we need to do some more simplification. I think this is fine, right?
Sir,
So am I correct? Have I done any mistake? You can tell me there is a mistake.
I don't think so.
Okay, good. So this is how we get the quadratic approximation then. And now let's. I think that should be fine for you guys to, you know, to understand how we go ahead and do the quadratic approximation. So we have done one single variable and one multivariable. So this can just be extrapolated for if there are more number of variables. So we'll discuss now the equality constraint. One problem that I think that I got from the internet, and the one problem that was discussed in class. So I felt that there was a slight mistake in what sir told in the end about the eigenvalues of that particular Hessian matrix. So we'll look into it, and before that we'll just get the will solve this problem. So it is a partial solution because I know making the Hessian matrix for this particular function, it's going to be a very tricky part, because the denominator, if you differentiate, it's just going to keep on increasing in the power. So we'll just get the optima points, and then we'll leave the problem till that point. Okay, so can you tell me, Jesurya, what will be the Lagrangian function for this particular optimization problem?
Egg, give me one second.
Yeah.
5 by x y square
Yes.
plus lambda times
Mhm.
x square plus y square minus 1.
Okay. So this seems correct. But what sir was telling, I don't know if you remember this, but it was when we have a constraint. that is gx is equal to b. So how do we bring this b to our side? Is b minus gx is equal to 0. Do you remember this?
Yes, sir, I remember.
So I think probably we should stick with what he is telling. Although this is not right, just the sign of lambda will change when we are solving it, and this is 100%
Okay.
correct. But let us just try to
Yeah, I
write.
found this online as well. I searched it somewhere and I found it this way.
Yeah, yeah. So when I also learned this Lagrange multiplier or Lagrange function, we also didn't do this particular thing. We also did the one which you suggested. But let's just
Yeah.
stick with with what sir is telling us for now. Yeah. So we have our Lagrange function, and at optima, what is the necessary or condition for optima? Yeah, necessary condition for any function. Let's call it fx. It has to be at optima at some x naught. Then what it should satisfy at x naught? Necessary condition, not the sufficient one.
The first differentiation should be zeros.
Correct. 100. So similarly, for this particular function also, the Lagrange function, the necessary condition will be that dl by dx will be 0, and x being the all the variables. So for this case, it will be dx and dl by dx 0, dl by dy 0, dl by d lambda is equal to 0, because lambda is also a variable, the value of which we don't know. That is correct.
Yes, sir.
Yeah. So now let's go ahead and solve this. So when we differentiate this particular function with respect to x, we get minus of 5 x square divided by x square y square and minus of 2 lambda x. Is this correct?
Yes, sir, it's correct.
Yeah. Then when we differentiate this with respect to y, so the minus 2 will go up and make minus 10, and it will be, so this is these are the two differentials. Now can you tell me what will be the answer for dl by d lambda?
Uh, 1 minus x square minus y square.
Correct, perfect. So this is these are the three equations, and we have three unknowns. Let's try to solve whether we can solve it or not. So straight away, what I see from these two expressions that I can eliminate lambda. So how do I do that? Is let me just,
Subtract one from other.
no. If we subtract, then you see x and y will
Oh,
be,
yeah, you multiply the coefficients. Was.
yeah, that also we can do, but let me show you this, and probably you can use this later on. This will be much more,
Okay, sir. Okay.
yeah. See, when we write this in this fashion, I think you will get the idea of what I am trying to say. Let me write this just now. What do you think I am trying to do here?
I'm trying to make one side equal or something.
uh, Partially true, but how I am going to do it is by dividing these two equations.
Okay.
So when we divide these, then you clearly directly eliminate this lambda, and you get x by y is equal to, minus minus is also cancelled, so 5 by x square y square, and then 10 x y cube. So you have to be a little bit careful when we are actually dividing this, but otherwise it is fairly straightforward. So 1 by 2 we can take out, and it will be y and x is equal to x by y. So basically y square by x square is equal to 2. We got one expression. This is correct?
So,
Yeah. Okay. And then when you use this expression into this equation, the constraint equation, then we have n minus x square, replacing y square with this value, minus 2x square is equal to 0. Can you tell me what will be the value of x? And let's assume that x and y both are greater than equal to 0. That is also one of the conditions. So can you tell me the a value of x?
1 by root 3.
Correct. And that of y?
Is it root 2 by root 3? Root 2 by 3.
Correct. So these are the two values of optima. And since only this particular thing was asked, so what is the point of optima? Later on, you can go ahead and try to find the root of Asian matrix minus this thing, and you can get the whether it is maximization problem or minimization problem. But this is the value of optima, where either it will be maximum or minimum. We can check later on. So yeah, so since this is going to be a much more difficult to find this Hessian matrix for this particular problem, because already we have so many things in the denominator, I will not go ahead with this problem. We'll discuss the problem that was discussed in the class, and we'll solve this particular problem nicely. Okay. So yeah, let's go ahead and yeah, did you watch the recorded videos, Jaysurya?
Yes, sir. I have watched it. I've tried to solve the assignments as well.
Okay, okay.
So,
So my understanding is there are some inequality constraint problems also in the assignments.
yes, sir. Yes, sir. I could only solve some one or some 3 or 4 questions. That's all this week.
Oh, okay, okay. So so don't worry. I think we have raised the complaint that inequality constraint is actually taught in the next week video. So probably these will. Um, so what is the deadline for your assignments?
This Wednesday, sir. 3 days more, I guess. 31st.
Oh, okay, okay. So probably maybe you can, yeah, maybe you can try to solve. If not, then we have already raised the complaint that these questions should not be included in this particular week. And let's see
Yes,
what.
sir. And they have released the next week's content as well.
Yeah, yeah. So I saw that, but but we cannot expect everyone to watch those videos and try to solve, right? Yeah. So
Yeah, yeah.
yeah. So okay. So NPTEL will deal with it. I think they have already removed some of the questions from previous 2, 3, 4 weeks based on our suggestions that were wrong, and you could not solve those questions. So these question also, let's see what happens.
Okay, sir.
Yeah. So let's solve this problem. So again, Lagrange for this particular problem will be x1 x2 lambda is equal to, so this is our particular function, and then we differentiate this with respect to x1. We get 2 minus lambda. So then sir said lambda is equal to 2, then dl by dx2 is 0. Then we get actually the differentiation 1 minus, sorry, I think it was 4 lambda x2. Am I correct?
Sir.
Yeah.
Yes.
So then x2 was 1 by 8, I guess. Yeah. And then we had dl by d lambda is equal to 0. So that's just this equality constraint being 0. And yeah, so then what was the value of x1? Can you tell me?
1 second, so I'm solving it.
Yeah, okay.
The 95 by 32.
95 by 32. Are you sure? Let me also just do a little bit of calculation. Yeah, it seems correct. So this is the value for x1. Now we have these values where the function is going to be optima. Now whether it is maxima or minima, let's try to find that out. So as I have also discussed in my previous videos, and I think this is where sir actually said only the eigenvalues, with maybe he missed saying the roots actually. So the Hessian matrix for this particular Lagrange multiplier, Lagrange function, let's say Lagrange function, is not it's not that straightforward. So I have in past sessions I have shared the slides where I have discussed thoroughly what is this Lagrange multiplier, how we get it. So maybe I will just show this to you in this class, and then yeah, okay. So let me just show this. Let me share my screen on this particular slide. Okay, it's 1 minute. Yeah. If I can, yes, I think I should be able to share the screen now. So is it, is
Yes,
my,
sir, I can see your screen.
okay, just 1 minute, I will show the PDF. Is this PDF visible?
Sir, constraint optimization.
Yeah, so constraint optimization with equality constraint. So this, yeah, so we had this L, we have the Lagrange function that is nothing but f plus lambda g. We are calling f our main function, and g is the constraint. So then this particular red highlight is the Hessian matrix that you normally get by differentiating, double differentiation with x in the diagonals, and then dx by d2f by dx dy and then so on. And this is the new part that we are actually going to add in this particular in this particular matrix. So what is this part is just nothing but differentiation of these constraints. So you write these constraints. Let's say if there are m constraints, you write them g1 g2 gm like this, and then you keep differentiate g1 with respect to x1 and then put it here, then g1 with respect to x2 and then put it here. So it's like dou g by dou g1 by dou x1 and dou g by dou g1 by dou x2, and then till the n variables, and then you do the same with the second constraint and the till the m constraints. And the red part now is nothing but the transpose of this particular thing that we have calculated. So let me just you can check the example that I have shown in my this week, I think it is week, let me just check, week second, I think. Yeah, week second video. So you can check that. Here we will just go ahead and make this for our problem. Just 1 minute, I'll share my screen again using the tab. Yeah. Okay, I hope it is visible.
Yes, sir.
Okay. So where is that? Yeah. So this is our Hessian matrix for Lagrange multiplier. So first let's make the normal Hessian matrix. So basically, let me write it like this itself. Yeah, let me explain it here itself. So we have our first differential dou L by dou x1, dou L by dou x2, and dou L by dou lambda, right? Now this matrix is nothing but you differentiate this by dou x1, x2, and we write it here. So we have our this function, that is dou L by dou x1. So when we differentiate this with x1, what will be the answer?
Uh, is it first difference, second differentiations?
Okay, so let me write it more clearly then. Okay, so there's some sort of problem. It is not. Oh, okay. Yeah. So we have dou L by dou x1, that was 2 minus lambda. Then dou L by dou x2, that was 1 minus 4 lambda x2. And dou L by dou lambda, that is 3 minus x1 minus 2 x2 square. So now if I differentiate this with respect to x1, what do you think I will get?
0.
Yeah, so that is the first entry of our modified Hessian. Then when I differentiate this with respect to x1, what will I get?
0.
Yeah, and then in this case we get,
-1.
yes. And the next entry is going to be differentiate this with respect to x2.
x2.
So it will be 0 again.
0.
And for
Minus
this,
4 lambda.
yes. And then here,
Minus 4x2
hmm. And then we differentiate this these things with lambda. So
lambda.
yeah, so here it will be
-1.
-1 and
Minus 4x2. 0.
yeah. So this is what is the modified Hessian matrix for Lagrange function. Now let's put the value of lambda x1 and x2 and get the actual thing. So 0, 0, -1, 0, and then lambda value is 2, I think. So it should be
Yes, sir.
-8, and x2 is 1
1 by
by
8.
8, so it will be minus
Minus 1 by 2.
0.5. And since it is symmetric, then we can just go ahead and write these things. So this is our particular modified Hessian matrix, right?
Yes, sir.
Yeah. So now what sir told was the eigenvalue of this particular matrix is going to decide uh, the nature of this function. But in
Yes.
actually what we have to do, the matrix that is actually going to, this is that matrix, yes, but how do we actually identify whether the function is of maxima or minima, is we have to do a solution for not the eigenvalue but a modified value which looks similar to the eigenvalue. So you subtract this variable, let's call it epsilon. You subtract this epsilon from the values of your normal Hessian matrix, diagonal values of your normal Hessian matrix. So you have 0 minus epsilon, minus 8 minus epsilon, 0, 0, and you leave other values as it is. And this is a new matrix that you will get. Is this clear?
Sir.
So when you put the determinant of this particular matrix to 0 and then you get the value of epsilon, then that value is going to decide whether the particular optimization function is a maxima or minima uh, for this value of x and y that we have gotten. So let's try to solve and see what is the value of epsilon that we get. So let's simplify this. So the matrix that we have is minus epsilon, 0, -1, 0, -8 minus epsilon. Then when we want to do the determinant, we have epsilon, and this multiplied by this is going to be 0 and minus of. So you can tell me the value of epsilon if you already calculated.
Sir, I have a doubt.
Yeah, ask me.
So why are we taking epsilon only for the first two diagonal elements, not for the third one? Because usually when we calculate eigenvalues, we take it for all three, right?
Yeah, so that's the thing. This is not the eigenvalue, or this epsilon is actually not the eigenvalue of this particular matrix. So that's what the mistake or the doubt that was this mistake in the class that sir discussed. I wanted to mention this particular thing is not a Hessian matrix. It is a modified Hessian matrix. So
Modification matrix, yeah.
so this is actually, if you see some online videos, it will be written as M and V transpose and 0. So this M being the Hessian matrix, V being the double differential of the constraints, and Vt is just the transpose and 0. So for our case, we had only one constraint. So our case, this is the V, and this is the V transpose, and this is the 0. So whether this particular matrix is positive definite or negative definite, that is going to tell us the nature of the function. But
Okay.
but to identify this thing, we have to make the determinant of this thing to 0. Sorry, yeah,
Epsilon.
with the epsilon at diagonal values. So that's why we multiply with the
Yes.
eigenvector identity matrix. So we have to
Got
put
it. Got it.
yeah. So you can tell me if you have solved the value of epsilon. Okay, let's solve it together then. So is this what you are getting? So Jesuri, were you able to solve it?
Yes, sir. So minus 6.4.
Yeah. So then the thing. So we have fortunately we got only one epsilon, but the situation, the conditions are if all the epsilons are negative, then we have a negative definite. This modified Hessian matrix is negative definite, and the problem is of maximization. When we have all the epsilon is positive, then we have it is a positive definite and it is a minimization. And if any of the epsilon is 0, then it is neither strictly maximization or minimization. So in this particular case, you will see that sir also got somewhere around this value. I don't know what went wrong there, and the problem then is of maximization. So I also was thinking when sir said that these things are actually the eigenvalues of minus 6.4 is the eigenvalue. You can actually put it into the internet or as normal calculator, and you can check the eigenvalues are not. There are three eigenvalues for this thing, and none of those
Yes, sir.
eigenvalues are actually coming to minus 6.4. So I think this is the approach to solve it. I thought I should mention it. And yeah, so that's all for today's session. Thank you, Surya, for your participation.
Thank you, sir. It was very good session.
Okay, thanks, man. I'll end the session then today.